let's talk about what negative exponents mean. We're going to talk about scientific notation at the same time, but let's kind of put this into context. So we're going to start with this right here, and we're going to kind of start in the middle of it actually. So let's start right here with the obvious 2 to the first power. Anything to the first power is itself. So 2 to the first power is simply 2, no surprises there. I'm going to move up. 2 squared, that means I have a couple 2s, so 2 times 2, and that of course is 4. Nobody's lost yet. But what we're doing with this is determining a pattern that we'll be able to use in order to figure out what happens down here. And we're going to use the same thing over here. We're going to do the same thing. So 2 to the third is 2 times 2 times 2. Well, 2 times 2 is 4, and we already knew that. By the way, though, we could have just used that 4 and then been like 4 times 2. Well, that gives me 8. And then 2 times 2 times 2 times 2 is going to give me, well, 8, if I just use 3 of them, see? 8 times 2, which will give me 16. So let's look at the pattern for just a second, and then we'll figure out what happens down here. So as I move up, my answer doubles every time. So I go from 2 to 4 to 8 to 16. So if I'm moving up, I'm doubling. If I'm moving down, well, what's the opposite of doubling? It's halving. So we're going to take half of everything as we move down. So half of 16 is 8, half of 8 is 4, half of 4 is 2, half of 2 is 1. Let's stop right there for a second. If I raise something to the 0 power, I'm going to get 1. It actually doesn't matter what I raise to the 0 power, I'll always get 1. The exception to that, and you don't have to write this down, but the exception to that is 0 itself. 0 to the 0 power is undetermined, undefined, nobody really knows what it is. We don't really know. So don't even worry about that one. But any other number other than 0, any real number other than 0 raised to the 0 power is 1. Okay, so let's continue. From 16 to 8, we took half. From here to here, we took half, took half, took half. Well, what's half of 1? Well, don't think too hard about it. Half of 1 is simply a half. And let's stop that thought right here. 2 to the negative 1, I'm going to put an understood number in our final answer, and that's going to start clarifying a few things. There's an understood 1 right here as an exponent. So let me go ahead and tell you what's happening. If I have a negative exponent, it moves the number that it's with, or variable, or whatever, from wherever it is to the other place. Let me clarify. Right now, this is kind of like one big numerator, and then we moved it down to the denominator. So let's keep going. If I have 16, take half, get 8. Half it, half it, half it, half it. Half of a half is a fourth. If you have half a pizza and I want half of it, then you would give me, well, you may not give it to me, but you would give me half of the half. You'd give me 1/4. And this is the same thing as having 1/2 squared. See, these are the same thing. So this negative exponent actually took what was here and sent it down to the denominator. Well, what denominator? Well, there wasn't really a denominator showing, so we had to make one. We sent that down to the denominator. And if we take half of that, we'd have 1 to the 8th power. And in case you need to know, that's 1/2 to the 3rd. You don't have to write this part. We don't have to put that right there. But we do need to understand that a negative exponent is going to move something down. So let me pause right here and just write a really quick example. If I gave you 5 to the negative 3, what that means is I'm going to take that 5 and I'm going to send it to the denominator. So this is the same thing as, oh my gosh, I need a denominator, 5, and that 3 goes down. It becomes positive. And what's in the numerator? Well, there's understood 1s everywhere, and there's an understood 1 right there. That's it right there. And we'll talk more about that when we get to the practice problems. Let's deal with the 10s really quickly. And these are going to come in handy when we have scientific notation. So let's start at the top, actually, and work our way down. 10 to the 4th power, that is 10 times 10 times 10 times 10. 10 times 10 times 10 times 10. You learned this back in the day. You could just count the zeros in a situation like this. And 10 to the 4th power, 4 tens, that's 100. That's 1,000 between all 3 of them. And then if I had 10 1,000s, then I'd have 10,000. So it's 10,000. Now, already you see the pattern. I just said it. We can count the number of zeros. If we're dealing with 10, we can count the zeros. So you already know the answer to this one is 1 with 3 zeros, which is 1,000. But if I wanted to, I could put 10 times 10 times 10. So that's 100. 100 times 10 is 1,000. So I have 1,000. Because we'll be dealing with very large numbers, I am going to put a lot of commas in this where necessary. So you'll see. Of course, every 3 digits we put a comma. So 10 squared, that's 10 times 10. And last time I checked, that was 100. If I had 10 $10 bills, I would have $100. And 10 to the first is just 10. 10 to the 0 is, okay. Anything, with the exception of 0 itself, any number, real number, to the 0 power is 1. Okay? So, 10 to the negative 1. All right, let's think about this. As I move down, I am taking a 0 off every time. Let's think about what I'm doing mathematically, though. I am dividing by 10 every time. If I had $10,000 and now I have 1,000, I would say, oh, I have a tenth of what I just had. Well, I probably wouldn't say that. I would probably be like, where'd my money go? But I would have a tenth of what I had just had, and then I would have a tenth again, and a tenth again, and a tenth again. Now I'm down to $1. Well, what's a tenth of $1? It's 10 cents. It's a dime. I'm going to put a leading 0, and it's that. Or I'm going to put equal marks. Or I could write it like that. It's 1/10. Okay, so let's hold that thought for just a second, because there's a negative 1 right there. And right now, that negative 1 sent the 10 to the bottom, and it's floating around up there. It's understood. You don't have to write it, but it's there. Okay? 10 to the negative 2, well, a tenth of a tenth, and that gets wordy, but let's think about it in terms of money. This is a dime. If you wanted to, you could put a 0 there and you'd have 10 cents. If I have a dime and somebody's like, hey, you got change for a dime, you could give them a tenth of a dime and you'd be giving them 1 cent, 1 penny. That is 1/100th of a dollar. That is the same as 1 over 10 squared. 10 squared is 100. And so, see what happened? That negative 2 moved that entire thing down to the denominator, and it was a positive. It's just one of those neat things that happens. You can write it like this as well, 1 over 100. 10 to the negative 3 is 1 over 1,000. It's the same thing as 1 over 10 to the third. And if you wanted to write it like a decimal, you could. And writing it like a decimal would make it tenths, hundredths, thousands. Tenths, hundredths, thousands, 10,000s. There we go. Tenths, hundredths, thousands. So that is, that's basically where negative exponents, or the explanation for why negative exponents work, and what exponents that are 0 do. But we're going to get into some of these practice problems really quickly. I'm going to take just a second and write them on the board. And as I do, I'm going to be talking about them. Feel free to pause this video at any point so you can get caught up on whatever you need to. Now, I'm not going to do all of these practice problems. The ones I don't do are up to you to finish. And this ink is not erasing, so I'm going to switch colors. I'm going to switch to green. Green somehow stands out on this, so we're going to do it. So I have 8 problems that I'm going to do. Let me go ahead and write them up here. I have 4 to the negative third. I have 6 to the negative 2. 7x to the negative 3. 5y to the negative 4. I'll write the other 4 in just a minute. Okay. If I have a negative exponent, it's going to move whatever it's with, number, variable, whatever, from wherever it is, numerator, denominator, to the other place. Looking at that right now, I don't even see a fraction. If you don't see a fraction, then it is a fraction, but technically it's over 1. You don't have to put that, but that's just my way of saying there's a basement waiting. This is the denominator, and it's waiting. So what I'm going to do instead is send, let's erase that whole fraction thing. I'm going to send 4 to the third to the denominator. And I have 4 to the third. And in a situation like this, I have to stop and ask myself, What is my numerator? My numerator right now is 1. How do you know? Because I have 1 over 4 to the third, and in case you care, there was an understood 1 right here, and that understood 1 is that. So, let me clarify the whole thing. This negative exponent is just going to send it downstairs, and in a situation like this, when in doubt, most of the time you can put a 1 to hold the place of whatever is not there. Okay, we're not quite done. Let's finish this a little bit. 4 to the third power, we're going to do it in our head. 4 times 4 times 4. I need 3 fours. 4 times 4 is 16. 16 times 4 is 64. So this is 1 over 64. There we go. There's your first one. Okay, the second one, same idea. You might already know the answer off the top of your head. But we're going to take that negative exponent and look at it and say, you have to go. You have to go downstairs. Right now, this is like sitting in some big kind of numerator thing, and we're going to send it to the denominator. So we have 6 squared in the denominator. When you move it, it becomes positive. So this negative exponent moved, became positive. There's a 1 in the top. Not just because I said so, but because there's an understood 1 in the front. And when in doubt, most of the time, you can just put a 1. Well, 6 squared, that would be 6 times 6. It's not 6 times 2. It's 6 times 6. That's 36. So this is 1 over 36. Okay. The next one is a little bit trickier. When we do this one, we have to be careful what we move. We only move upstairs, downstairs, numerator, denominator, the thing that has a negative exponent. The x has the negative exponent. The 7 does not move. It stays exactly where it is. Well, where is it? Upstairs. It's already in the numerator. So as I look at this problem, I'm thinking, who stays? Who moves? 7 will stay. It doesn't have a negative exponent. It does not move. The x has a negative exponent. It moves. There we go. The next problem, you can probably already guess what the answer is. It's exactly like the last one. So let me explain it. I'm going to try to explain it in a slightly different way. I'll try. It may come out being the same thing. But negative exponents move things. Negative exponents move things. The y has a negative exponent, so it moves. The 5 does not have a negative exponent. In case you care, the 5 has a positive 1 that's kind of understood as an exponent, so it stays exactly where it is. Okay, those are the first 4. I'm going to do the next row as well, and then after that you may want to pause the video so you can do the front side, then you can flip it over and we'll start with the back. Okay, now it's going to get crazy. I'm going to write these one at a time because I might need a little extra space. 3 to the negative 1 plus 2 to the negative 1. What in the world? What in the world? Okay, let's start by moving things. Negative exponents move things from numerator to denominator, or if they happen to be in the denominator, they'll move into the numerator. So, 3 to the negative 1 becomes, now ignore this. I'm actually going to erase it. This isn't our concern right now. We're going to do one piece at a time. 3 to the negative 1 becomes 3 to the 1 in the bottom. There is a positive 1 now because we moved our negative exponent from where it was to where it needed to be so it could become positive. We have an understood 1 in the top. I'm going to erase this exponent right here because it's kind of unnecessary. It's there. It's a positive 1. This was made positive. Okay, let's do the next part. We have this. We are going to add this next part. So we have 2 to the negative 1 power. This negative exponent is going to move the 2 into the denominator. And when it moves, the exponent becomes positive. I don't have to put the understood 1 there, but I could if I wanted to. All right. I need a numerator. My numerator right now is an understood 1. Okay? Not to confuse you, but I just want to throw in one little thing real quick. There's an understood 1 right here and an understood 1 right there. That is your numerator. That is your numerator. There's all kinds of understood 1s floating around everywhere. We don't always have to put them though. Okay. So we need to add these two fractions. When we add fractions, what do we need? Common denominator. Common denominator between 3 and 2. What? The 3 and 2 go into. Now what goes into them? What do they go into? That would be a 6. 3 goes into 6. 2 goes into 6. To turn a 3 into a 6, you multiply by 2. 1 times 2 is 2. To turn a 2 into a 6, you multiply by 3. 1 times 3 is 3. Let's add. 3 and 2 added together gives me 5 over 6. There we go. That doesn't reduce, nor is it an improper fraction, so we're good to go. All right. Pause it if you need to. Actually, I would recommend that if necessary, you pause it right now and find other problems that look like that and tackle them now that this is fresh on your mind. That might be a good idea. However, the next one is just like it, so let's do it. I'm going to go a little bit faster though. 4 to the negative 1 plus 4 to the negative 2. Okay, this plus sign is breaking things up, so we're going to do this in 2 separate pieces. We're going to find out what 4 to the negative 1 is. I'm not even going to explain it. I'm just going to write it. See it? Now you see it? Became positive, moved downstairs. This becomes positive, goes down as well. Okay, now if you're wondering where these 1s come from, they were always there. They were just hanging around in front. It was like 1 times whatever. It's understood, it's just there. It's a placeholder. I don't always need that placeholder. Sometimes the number's already there, and it's not just an understood 1. Anyway, I digress. What I want to do is add these two fractions. When I add these two fractions, I need a common denominator. Before I can get a common denominator, I may want to look at that and say, you know what? I know what 4 squared is. 16. 4 to the first is just, well, 4. Now I'll get a common denominator. Okay, what does 4 go into that 16 goes into? 16. 16 goes into itself evenly. 4 goes into it, well, 14 goes, tongue got tied. 16 goes into itself. 4 goes into 16. Common denominator is 16. To turn a 4 into a 16, you multiply by 4. 1 times 4 is 4. To turn a 16 into a 16, you don't do anything. You could multiply by 1. 1 times 1 is 1. 4 plus 1 is 5 over 16. All right, I'm going to do 2 more on the front. The rest of the front is up to you. Then we'll do some on the back. 5 to the negative third, 7 to the negative 2. At this point, I think you understand these pretty well, so we won't spend too much time on these. 5 to the negative 3 and 7 to the negative 2. Okay, I haven't explained it completely like this yet, but I'm going to go out on a limb here and I'm going to say, hey look, understood 1. Might help, just because I felt like it. That understood 1 has an exponent of an understood 1. If that doesn't help you, then just ignore this. But the exponent of an understood positive 1 keeps this from moving. It's still in the numerator. This, however, moves to the denominator because it has a negative exponent. We have 5 to the third. 1 over 5 to the third. If this understood 1 business made no sense, you can just erase it. Move this to the bottom and be like, hey, I need something to hold its place, and it's a 1. Okay, 5 to the third. Here we go. I'm not going to do this in my head. I know the answer, and you might know the answer too. So I have 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is, what is it? Goodness. That was terrible, wasn't it? 25 times 5. Well, let's do it. 25 times 5. 5 times 5 is 25. 2 times 5 is 10. 10 plus 2 is 12. 125. That sounds like Bob Dylan. 125. Tell me, how does it feel to be on your own? It's like a rolling stone. You know that song is ridiculously long and it doesn't have a bridge or anything? People didn't think it would be a hit, and it was. All right, 7 to the negative 2 means I need to move my 7. And it goes to the denominator. and it becomes a positive exponent. There's a 1 that's holding its place up there. So 7 squared is 49. There we go. All right. I recommend that you pause the video here, finish the front side, compare the types of problems to the ones that you've already seen and know how to do, and then we will talk about some stuff on the back side in just a few minutes. Keep the video playing if you want to keep going. So I'm going to erase this. Let's talk about scientific notation. We're on the back side now. And this next little section is going to lead us into scientific notation. So we have 5 times 1,000. Well, you know what that is, but that helps us prove a point. So we're going to have 5 times 1,000. If I won $1,000 5 times, then that would be nice. And I would have how much money? This one's fairly obvious. I'd have $5,000. Okay, I'm proving a point with this, and here's the point that I'm proving. Watch this. There's a decimal right there. See it? 5.0. It's there, whether you realize it or not. There's a lot of understood stuff floating around in this stuff. So 5 point whatever. And it's 5 times 1,000. Let's see what happened to the decimal. There it was. But it moved, now it's here, and it moved 1, 2, 3 places because I had 1, 2, 3 zeros because this is 10 to the 3rd power. We'll revisit that in just a second. Let's just keep moving. We have 7.3 times 100. 7.3 times 100. If I did 7.3 times 100, all I need to do is move my decimal a couple places. And okay, let's think about it in terms of money. If I had $7.3, $7.30, 100 times, then I would have $730. So here's my decimal, 7.3, and this is not just 100, this is really, check this out, this is really 10 squared. And I'm going to move my decimal 2 places. Just like this was 10 cubed, and I moved my decimal 3 places, and this is why scientific notation is so incredibly practical when we're dealing with enormous numbers that are, well, huge numbers, or actually ridiculously small amounts as well. So I'm going to make this move 2 places, make the decimal move 2 places. So 1, 2, again, there we go, 730.0 or whatever. That's what it is. The next one is 2.893 times, I should have put some commas in there, but I didn't, it's a million. 2.893 times 1 million. 1 million has 6 zeros. I counted that right, didn't I? Yeah, I did. A million has 6 zeros. So what we're going to do is take 2.893 and we're going to move our decimal place 6 times because this is the same thing as 10 to the 6th power. That's going to come in handy in just a second. So we're going to move 1, 2, 3, 4, 5, 6. I'm going to write that down just a little bit differently just so it kind of gets cleaned up. So 2, 8, 9, 3, 0, 0, 0. Put some commas. That is $2,893,000 or llamas or whatever it is. Okay, the next one. 3 times 10 to the 4. 3 times 10 to the 4. Well, 10 times 3 to the 4. What in the world is 10 times 3 to the 4? I'm glad you asked. This is the same thing as 3 times 1. 0, 0, 0, 0. 4 of them. And that means I'm going to move my decimal over 4 places. Here's my decimal right now. Glasses keep sliding down. Here's my decimal right there. And I'm going to move it 4 places. So 3, 0, 0, 0, 0. And it makes sense. 3 times 10,000 is, well, 30,000. There we go. This is scientific notation. And you've seen it before, I'm sure. It's basically a way that we express very large amounts. Because no one really wants to write a number like that all the time, particularly if it was much bigger than that, like our national debt, which we'll get to that in just a minute. So 8.2 times 10 to the 5. 8.2 times 10 to the 5. So how many decimal places am I going to move? Well, 5. So I have 8.2. There's my decimal. I'm going to move it 5 places. I'm going to go that direction with it. You'll find out why in a minute. So 1, 2, 3, 4, 5. I'm sitting down on this desk and I'm about to fall. That'd be embarrassing, wouldn't it? I wouldn't edit it out either. I'd leave it in the video. 820,000. I'm going to rewrite it just to make it look cleaner. 820,000. Okay, now we're going to throw in a negative exponent just to make you angry. 3 times 10 to the negative 4. 3 times 10 to the negative 4. Now we know what negative exponents do. If we're going to put this in context with the stuff that we did on the front side, we would say, well, that's 1 over 10 to the 4th, and that is correct. That is absolutely correct. But let's actually not go there. When I have a positive exponent with my scientific notation, I send it this way. Send my decimal to the right. When I have a negative exponent, I send it to the left. So what I really have right now is 3 point, and I'm going to send that decimal 4 places this way. I'm going to prove why this works in a second. So 1, 2, 3, 4. There we go. 0.0003. I'm going to put a leading 0 in the front just because it looks neater. Let's read this the way it really is. 3 10,000ths. Tenths, hundreds, thousands, 10,000ths. 3 10,000ths. All right, let's kind of wallow in this for just a second. 10 to the negative 4, that's the same thing as saying 1 over 10 to the 4. 3 10,000ths. Same thing. Same thing. All right. So right there below it, it says scientific notation, and there's a definition for it. But what I'm going to write is going to be my own definition of scientific notation. Let me erase part of this. And then we'll do just a handful of them, and then I'm going to let you finish. I'm going to switch to the blue marker. It doesn't always show up well, but we'll give it a shot. So, scientific notation. Scientific notation is a way to express very large or very small, forgot how to make a B, very small values. And there's kind of a format to it. It needs to be some number. I'm going to call it A, then times 10 to the n. Now, don't panic when you see a bunch of letters in with your math. You've seen variables before, you know what this means. But I'm going to clarify what all this is. A is between 1 and 10. And if I want to get more specific, I could say that A could be 1 but not 10. I'm going to go there. Let me go there mathematically for just a second. So A is going to be less than 10, but A is also going to be greater than or equal to 1. And I know I said greater than or equal to while I wrote the less than or equal to sign. I was kind of reading it backwards as I was thinking of it. Here's what I really mean. A is between 1 and 10. What I'm really trying to say is, in scientific notation, you'll never see, if it's proper, you'll never see 976 times 10 to the 4. You won't see that. What you'll see instead is 9.76 times 10 to the whatever. They'll never put the zero, or they'll never put the decimal anywhere but after the first digit. Now, just to be clear, A could be negative, but we're going to pretend right now like they're all positive. We're not really going to delve into that. And n is an integer. In other words, no one's going to pull a fast one on you and say, oh, n could be 1/2. Well, don't, because then, don't write this down. Because then it would be something like 4 times 10 to the 1/2. Well, what in the world does that mean? Well, actually, that means the square root of 10, but we're not going to go there. That needs to be an integer, not a fraction, not a decimal. It just needs to be a whole number or a negative number. All right, so then we have a few examples in the next little section, and I'm going to do the word problems, so to speak. So we're going to write the things in scientific notation that need to be in scientific notation and the ones in standard that need to be in standard form. So The Pioneer spacecraft is a spacecraft that was launched many, many years ago. It's Pioneer 10. The Pioneer 10 spacecraft sent its last signal. It was 8 times 10 to the 9th miles from Earth. Okay, now I'm not going to deal with the number 10 in that. Pioneer 10, that's not the number I'm dealing with, obviously. I'm dealing with this one, 8 times 10 to the 9th. That is indeed in scientific notation, for obvious reasons. That is an integer, that's a number between 1 and 10. And so there's my decimal. And so I'm going to go 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom, 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 boom. How far is that? Pretty daggone far. Further than I've ever traveled. All right, so how far is that? Let's put some commas and find out. Hundreds, thousands, millions, billions. 8 billion. Quite a bit. Okay. There are over 1.5 times 10 to the 6th species of life forms on Earth. That includes animal life, plant life, bacteria, fungi, things like that. Fun guy, not like, hey, there's a fun guy, like funguses. That was a bad joke, wasn't it? Most people aren't liking my jokes. That was a pun. A lichen is a type of fungi. Okay, anyway. So here's my decimal. How about I do math? Here's my decimal. I'm going to move it 6 places. So 1.5, 1, 2, 3, 4, 5, 6. Pew, 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 pew. I'm going to erase all that pewing. And as I erase that, the number that I'm dealing with emerges, and it is that 1.5 million. 1.5 million different species of life forms on Earth. Even the fun guy. A hydrogen atom is really, 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 really small. Clearly not seen with the naked eye. Incredibly, incredibly small. It's actually the smallest atom there is. Hydrogen is the lightest element and the most abundant element in the universe. Okay, so where's our decimal right now? There. All right, well, what are we going to do to it? We're going to move it 10 times. Not to the right, it's to the left. All of a sudden, Beyonce walks in and she said, never mind. That was another bad joke. It's been a long day. So 5, there's my decimal. We're going to move it 10 places this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not going to put commas in this, but I am going to tell you what it is. This is crazy. Check this out. This is cool. Well, let me erase all this. Okay. There it is. I'm going to put a leading 0 just because. Well, first of all, let's put this in perspective. This is the width, the average width of a hydrogen atom. And this is in terms of meters. And this is a meter. So it's really, 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 really small. Okay, so I got, bear with me, tenths, hundreds, thousands, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billionths, 10 billionths. This is 5 10 billionths of a meter wide. If I could divide this into billionths, and take 5 of them, that would be approximately the width of a hydrogen atom. Okay, so I have just done those 3. If you want to pause the video here and tackle the rest of those, you can. I'm going to go to the next section where it says convert these numbers into scientific notation, and then I want to deal with the one that says the sun is so many miles from Earth and the moon and the average gnat weighs so much, that kind of thing. Okay, so pause it if you would like to, and if you want to go ahead and do the next section, or if you want to just keep following with me, you can do that as well. So the sun is 93 million miles from Earth. 93 million miles from Earth. There it is. Okay, this is what it is. This is what I want my decimal to be. I want it to say that. Times 10 to the what? Now you might know off the top of your head, but just in case you don't, let's count. Let's grab the green marker and let's start counting. This is where I want my decimal to be. This is where it is. I'm going to take it from where I want it to be to where it is, and I'll be going in the right direction if I do that. So 1, 2, 3, 4, 5, 6, 7. There we go. This is the distance between the sun and the Earth. And when you're dealing with distances this large, a lot of astronomers do this, they use scientific notation because it's just a lot more practical. The moon is 238,900 miles from Earth. Which, by the way, because of the speed of light, it takes about 1 second, approximately 1 second, for light to reach Earth from the moon. Just saying. It's kind of cool. Actually, we see the sun as it was 8 minutes ago. Like if the sun was to explode, we wouldn't know it for 8 minutes. We'd have 8 minutes left to live and we have no idea. Isn't that neat? Isn't that kind of scary? All right, so, wow, thanks for that, Mr. Reader. What we really want is 2.389, let's drop off those zeros, we don't need them, times 10 to the what? Okay, I'm going to put my decimal where I want it to be and move it to where it is, and that'll tell me what my exponent is. So, there. 1, 2, 3, 4, 5. There it is. I'm going to write it in green just so it doesn't match. There we go. Driving you crazy too, isn't it? Oh, drop my marker. Okay. The average gnat weighs, wow, I'm going to read that number the way it really is. 600,000, 10,000, 529 hundred-thousandths of an ounce. That's small. Well, that's light. It is small, but it's light also. 3, 4. A lot of things are light that aren't small, and a lot of things are small that aren't light. This is where it is. This is where I want it to be. I want it to be after that first non-zero digit. I want it to be 5.29 times 10 to the what? Okay, so I'm going to move my decimal from where I want it to be to where it is, and that tells me how many places I would have to move it. So I'm going to go 1, 2, 3, 4, 5. There we go. 5, right? No. I went to the left, everything you want, never mind. I went to the left, therefore it's -5. Okay, the rest of this sheet is up to you. When you get to the very last problem about our national debt, it gets really depressing. I recommend that you write out the number 20.1 trillion. Like, it'll scare you to death when you think about the fact that you're going to have to pay that off. But anyway, write out 20.1 trillion like as a decimal, and then see, like count from there to see where you need to move it.